In the previous video, we saw that the work that we need to do in order to assemble n number of charges was equal to half times the summation of I goes from 1 to n, the charge q of I times the potential at the point where charge qi is located, that is r of I. This is for a point charge distribution. Point charges. Now what if we had continuous charge distribution? Let's say like this. The charges are distributed in a volume inside this region. Then how would we write the work done in that case? And that we also know that the volume charge density is equal to the dq divided by d tau, where dq is small charge element divided by d tau, which is small volume element. So we will take a small volume element in the form of a cube. Let's draw our axis and let the position of this volume element be r prime. That is, the distance of this volume element from the origin O will be r prime. And let's call this volume of the small volume element as d tau prime. Prime because these will be our integrating variables. And we already know rho, which is the volume charge density. So now if we multiply rho times d tau prime, we will get a small charge element dq. And when we integrate this over the entire volume, we will get the charges. So essentially, we are just converting the summation into an integral. And what will be the potential in this case? In the case of continuous charge distribution? Now in integral, we implicitly assume that we will take the limit for this d tau to go to 0. So when we are integrating, this d tau goes to 0. Now to find the potential, as this d tau volume will go to 0, it will essentially be reduced to a point. So we will need to find the potential at this point, which will be just the potential due to the entire configuration at that point Ri. So the potential will be potential due to the point r, or r prime as in this case. So we can now do the entire conversion for continuous charge distribution. It will be, work done will be equal to half, summation becomes integral over the volume in which the charges are located, that is over this entire volume in which the charges are located. It will be equal to rho d tau prime v. Now in theory, we are done. This is the formula that we can use when we have continuous charge distribution. But notice that we have rho, which corresponds to charges, and we have potential, which corresponds to the electric field. So we have charges multiplied by the field. Now we will convert this equation entirely in terms of the field. So notice that you can use Gauss's law, which is divergence of the electric field is equal to rho by epsilon naught. So we can solve for rho. Rho will be equal to divergence of electric field times epsilon naught. So we can write it as a half integral of, we will take the epsilon outside since it is also a constant, divergence of the electric field times the potential times d tau, and we will integrate it over the entire volume in which the charges are located. Now let us simplify this part. We know that there is a vector identity, which is the divergence of an vector times a scalar. In this case, vector will be a and phi is a scalar, will be equal to the vector times the gradient of the scalar. Gradient is a vector, that is why I am writing the vector symbol, plus the divergence of that vector field times phi. Now in our case, the vector will be the electric field and phi will be the potential, which is a scalar. So we can write it as divergence of electric field times the potential will be equal to electric field dot gradient of the potential plus divergence of electric field times the potential. Now notice that this is what this term is, this term over here. So we can further write it as divergence of electric field times the potential is equal to divergence of electric field times V minus the electric field dot the gradient of the potential. Now, we know that electric field is equal to the negative gradient of potential. So this will further reduce to divergence of electric field times potential minus times minus becomes plus. This will be the magnitude of the electric field the whole square, since the electric field is negative gradient of potential, and this term times this is just the magnitude of the electric field the whole square, and minus minus becomes plus. So instead of this term, we can write this inside our integral. So the integral work done becomes half integral of, again it will still be a volume integral, divergence of electric field times V deta plus again the volume integral of E square. I am not putting the vector symbol since now it is the magnitude of the electric field deta. Now we have the vector electric field times a scalar, which is V, and a vector times a scalar is again a vector. So here we will make use of Gauss's divergence theorem. Which says that the volume integral of divergence of any vector field is equal to closed surface integral of that field, and the vector field in our case will be the electric field vector times the potential. So we can convert del dot E times V into a closed surface integral of E vector times V. Here it will be a dot product, so again dot dA. Now we will substitute this over here. So again work done will be equal to half closed surface integral of electric field times V dot dA plus the volume integral of magnitude of electric field the whole square deta. Now what is the region over which we are performing this integration? Now we perform this integration for the entire region and the volume which contains the charge distribution. But we can take an even bigger region. The only condition is that the charge containing region should be enclosed within the surface of this outer region. So if the charges are located inside this, let's say this is the region that will integrate, it will not matter, since if we go back to our original work done formula, which was half integral rho deta V. Now in the outer region, rho is equal to 0. So when we integrate from here to here, we will have some value for this integral. But when we integrate from here to outside, the rho is equal to 0. So this entire integral will then be equal to 0. So there will be no contribution. Essentially, we can take any big surface or region that we want. The only condition is that we should enclose the charges within that region. So now, let us see what happens to this integral as we increase our radius of our region. So we have surface integral of electric field times V dot dA. Now let's say we took a sphere. Now the charges are located in this region, and let's say we take a very big region or a volume like this. Now increase the volume to be very big. Then as compared to this big volume, this will be a point charge, and we know that for point charges the electric field drops or reduces by a factor of 1 over r square, and the potential by a factor of 1 over r, and since we took spherical region, the area of a sphere will be equal to 4 pi r square, so the area will increase by r square. And as we increase the region, let us take the total contribution of everything. Let us forget the constants and let us only calculate the r dependence. So it will be 1 over r square times 1 over r times r square. R square get cancelled, and this integral E times V dot dA will change as 1 over r as we increase our volume. And now if you extend the volume all the way to the outer space, that is all the way to infinity, so it will change by 1 over infinity, which is equal to 0. So as we integrate over the entire space, this integral goes to 0. And this integral, originally we were integrating it over the volume in which the charges were located, but now we will integrate it over all space. So our work done now becomes half. This integral goes to 0, so 0 plus all space. We are integrating over all space, e square d tau. So our work done will be equal to half integral. We are integrating it over all space, that is the entire space, e square d tau. So this is a final formula. We also call this as the energy density of electric field. Since here we are considering only the electric field and no charges, this formula is also correct, and the original formula, which was this one, is also correct. Both are correct. It depends on us which one that we want to use. If we know the electric field at all points in space, then we can easily use this formula and get done with our problem in a matter of seconds.